In this lecture, we study Siamese network. The name Siamese is an analogy to Siamese twins. Siamese twins mean two babies born physically connected to each other. I will introduce two ways of training Siamese networks. The first method is learning pairwise similarity scores. You can read the two papers listed below for more details. The Siamese network needs to be trained using a big data set. The data are labeled. Each class contains many samples. We need to prepare positive samples and negative samples using the training set. Positive samples tell the model what kind of things are of the same kind. Negative samples tell what are different kinds. Positive samples are obtained in this way. Randomly sample an image from the training set. For example, we get this tiger. Then sample another image from the same class. We get another tiger. This is a positive sample pair, and we label it as 1. It means the two are of the same kind. We can do the same to get 2 cars and 2 elephants. The labels of the pairs are 1s. Negative samples are constructed in this way. Randomly sample an image from the entire training set. For example, we get this car. Then, exclude the car class and randomly sample an image from the rest of the training set. For example, we get this elephant. Label the pair as 0. 0 means the 2 images are different. Do the same and get negative sample pairs such as the husky and tiger pair, the elephant and macaw pair. Label the negative pairs as 0s. Let's build a convolutional neural network for feature extraction. The neural network can have convolutional layers, pooling layers, and a flattened layer. The input is an image. Denote the input image by x. The output is the feature vector. Denote the output feature vector by f of x. Let's train the neural network using the training data we have prepared. We have prepared many pairs such as the 2 tigers as well as their labels. The tigers are from the same class, so the label of this pair is 1. The 2 tigers are the input of the neural network. The convolutional neural network we built a minute ago is denoted by function f. The neural network outputs 2 feature vectors extracted from the 2 input images. The feature vectors of the 2 images are denoted by h sub 1 and h sub 2. I want to emphasize that there is only one convolutional neural network for feature extraction. The 2 f functions are the same neural network we built. Then, calculate h sub 1 minus h sub 2. The result is a vector. Take the absolute value of every entry in the vector. Let the result be vector z. Z is the difference between the 2 feature vectors. Then, use several dense layers to process the z vector. The output of the layers is a scalar. Finally, apply the sigmoid activation function upon the scalar and obtain a number between 0 and 1. The final output measures the similarity between the 2 inputs. If the 2 input images are from the same class, then the output should be close to 1. Otherwise, if the input images are from different classes, then the output should be close to 0. By looking at the network structure, you can easily understand why the network is called Siamese network. Siamese twins are connected to each other. In the figure, the twins have their own bodies, but their heads are connected. We have previously prepared the label. The two images are both tigers, so the label is 1. We set 1 at the target. We hope the scalar output by the network is close to the target 1. We use a loss function to measure the difference between the target and the predicted scalar. The loss can be the cross entropy of the target and the prediction. It measures the difference between the two. Having the loss, we can use backpropagation for calculating the gradients. Then we perform gradient descent to update the model parameters. The model has 2 parts. One is the convolutional neural network, denoted by F. It is for extracting features from the input images. Note that the 2 Fs are exactly the same convolutional neural network. They have the same model parameters. The other part is the fully connected layers, which map vector z to a scalar between 0 and 1. During training, both parts will be updated. Using backpropagation, the gradient flows from the loss function to vector z and the parameters of the dense layers. Knowing the gradient of the loss with respect to the dense layers parameters, we can update the parameters by a gradient descent. Further propagate gradient from the vector z to the convolutional neural network F. Then, we can use the gradient to update the parameters of the convolutional layers. To this end, we have performed 1 round of update. To train the model, we prepare the same number of positive samples and negative samples. Negative samples mean the 2 images are different objects. The pair of negative sample is labeled as 0. We hope the prediction by the network is close to 0, which means the network knows the 2 inputs are different. Then, do the same as before to propagate gradient from the loss to dense layers and the convolutional layers to update the model parameters. After training the model, we can use a model for one-shot prediction. In this example, the support set is 6-way one-shot. There are 6 classes. Each class has 1 sample. Note that the 6 classes are not in the training set, which is why few-shot learning is difficult. Now we have a query. We know the query must be among the 6 classes in the support set. We need to choose 1 out of the 6 classes. We can compare the query image with the images in the support set 1 by 1. Taking the query and the fox as input, the Siamese network predicts a score between 0 and 1. Then we know the similarity between the query and fox is 0.2. Then compare the query image with the squirrel and get a similarity score of 0.9. Do the same to find all the similarity scores. Then identify the largest among the similarity scores. We found the query most similar to squirrel. The similarity score is 0.9. So we predict that the query is a squirrel. We have trained a Siamese network for computing pairwise similarity scores. Next, let's study another method for training the Siamese network. The method is triplet loss. We prepare the training data in a different way. Having such a training set, each time we need to select 3 images as a training sample. It works in 3 steps. First, randomly select an image from the entire training set as the anchor. For example, this tiger is selected. It becomes the anchor. Record the anchor. Then, from the same class, randomly select an image as positive sample. We got another tiger. Record the positive sample. The positive sample and the anchor are from the same class. Lastly, exclude the tiger class and randomly sample an image from the rest of the training set as a negative sample. We happen to get this elephant. Record the negative sample. The negative sample and the anchor are from different classes. To this end, we have an anchor XA, a positive sample X positive, and a negative sample X negative. Feed the three images to the convolutional neural network F. Although the name is Siamese network, there is only one convolutional neural network. The three Fs are the same neural network. The convolutional neural network extracts three feature vectors from the three images. Calculate the distance between the positive sample and the anchor in the feature space. Let d positive be the square distance. It is the squared L2 norm of fx positive minus fxa. We do the same to find the distance between the negative sample and the anchor in the feature space. Let d negative be the squared L2 norm of fxa minus fx negative. We hope the learned network F has such a property. The feature vectors from the same class are nearby, while feature vectors from different classes can be well separated. Thus, d positive should be small, because the positive sample and the anchor belong to the same class. D negative should be large, because the negative samples and the anchor are from different classes. I want to reiterate the relation among the three samples. This is the feature space. The convolutional neural network maps images to feature vectors. This is the anchor. It is a tiger image. Its feature vector is the red dot. This is a positive sample. It's another tiger. Its feature vector is the green dot. The square distance between the two feature vectors is d positive. We hope d positive is as small as possible. The elephant is a negative sample. It's from a different class. Its feature vector is the blue dot. The blue dot is the feature vector extracted by the convolutional neural network. Let d negative be the square distance between the blue and red feature vectors. It means how different the negative sample is from the anchor. We hope d negative is as large as possible. D negative should be much larger than d positive. Otherwise, the model cannot distinguish between tiger and elephant. Based on the idea we discussed, let's define the loss function. D positive is the squared L2 distance between the positive sample and the anchor in the feature space. Intuitively speaking, the feature vectors of two tigers should be close, so we should encourage d positive to be small. D negative is the squared L2 distance between the negative sample and the anchor in the feature space. We hope the feature vectors of different classes are far apart. The feature vector of an elephant should be far from tigers. We thereby encourage the distance d negative to be big. We can define a margin, alpha. Alpha is positive. it is a tuning hyperparameter. Ideally, the negative is big and the positive is small. In our example, the negative is the distance between an elephant and a tiger, while the positive is the distance between two tigers. The negative should be much larger than the positive. If the negative is greater than the positive by a margin of alpha, then we believe the classification is correct and the loss is zero. If the condition is not satisfied, which means the negative is not sufficiently larger than the positive, then we believe this is a failure. The model cannot tell the difference between an elephant and a tiger. There should be a loss. Let the loss be the positive plus alpha minus the negative. We encourage the loss to be small. A small loss means the positive is small, so the two tigers are close in the feature space. Also, a small loss means the negative is big, so the tiger and elephant can be well separated. In sum, we define such a loss function. If the positive plus alpha minus the negative is greater than zero, then it is a loss. It means we cannot distinguish between an elephant and a tiger. Otherwise, if the positive plus alpha minus the negative is less than zero, which means the classification is right, then there is no loss. The loss is simply zero. Such a loss function is called a triplet loss. It is based on a triplet of samples: the anchor, the positive sample, and the negative sample. With the loss function at hand, we can take the derivative of the loss with respect to the model parameters, and then perform gradient descent to update the model parameters. After an update, the elephant and the tiger will be further apart in the feature space, whereas the tigers will be closer in the feature space. After training the Siamese network, we can use the network for one-shot prediction. We are given a support set. The classes in the support set are not contained in the training set. We are given a query image. It belongs to one of the 6 classes in the support set. We want to classify the query image. We compare the query image with the images in the support set in this way. We use a convolutional neural network to extract features from all the images. Then, compute the distance between the feature vectors. For example, the query and the fox have a distance of 231 in the feature space. The query image and squirrel have a distance of 19 in the feature space. Do the same to compute all the distances. Then find the smallest distance. The distance between the query image and the squirrel class is 19. 19 is the smallest among all the distances. The model believes the query image is most similar to the squirrel class. The model thereby predicts that the query image is a squirrel. In this lecture, we learned the Siamese networks for solving few-shot learning. Let me summarize this lecture. Here is the basic idea of solving few-shot learning. We first train a Siamese network on a large-scale training set. The Siamese network learns the similarity and difference between things. After training, we can use the Siamese network to make predictions. What makes few-shot learning different from standard supervised learning is that the queries class does not appear in the training set. For example, the query is a squirrel, but the training set does not have a squirrel class. Thus, to recognize the query, we must provide additional information. The additional information is a support set. The support set is called k-way n-shot. K-way means the support set has k classes. The more classes there are, the harder the prediction is. N-shot means each class has n samples. The fewer samples there are, the harder the prediction is. The hardest problem is one-shot learning. That is, making a prediction based on only one sample. With the trained Siamese network at hand, we can compare the query with every sample in the support set to find similarity scores. Then, use the sample in the support set that has the highest similarity score as a prediction. I have elaborated on two ways of training the Siamese network. One is using the Siamese network to predict the pairwise similarity score. Each time, we select a pair of two images as the input of the Siamese network. The images are transformed by convolutional layers and dense layers. The output is the similarity score between 0 and 1. 1 means the two inputs are from the same class. 0 means the two inputs are different. The target is either 0 or 1. If the two inputs are from the same class, then the target is 1. Otherwise, the target is 0. Define the loss function as the difference between the prediction and the target. The goal of training is to minimize the loss, equivalently making the prediction closer to the target. In this way, the learned neural network can predict the similarity between the two inputs. The other way of training the Siamese network is to use the triplet loss. Each time, select 3 images as inputs. They are the anchor XA, the positive sample X positive, and the negative sample X negative. Then use a convolutional neural network to extract features from the inputs. We obtain 3 feature vectors. Let d positive be the square distance between the positive sample and the anchor in the feature space. Let d negative be the squared distance between the negative sample and the anchor. The objective of training is to make d positive as small as possible. That is to make the two tigers close in the feature space. Also, make d negative as big as possible. That is to make the tiger far from the elephant in the feature space. With the trained network at hand, we can compare the query image and the labeled image in the feature space. Prediction is made based on the distances in the feature space. I have finished teaching Siamese networks. Thank you for watching this video. The link to my slides can be found below the video. In the next lecture, I will introduce pre-training and fine-tuning for few-shot learning.